Time value of money is one of the most basic and pervasive concepts in all of modern finance. And if you're watching this video, hopefully you have also got some version of this, what I call the Snowball Sheet, which I will use more or less and follow in this video. As the sheet indicates, there are four basic applications to time value of money. The future value of a lump sum, better known as the future value of a dollar, present value of a dollar, future value of an annuity, and present value of annuity. We'll describe those all as we go along, but it's really important that you have this sheet before you, because one thing that's going to be very important is becoming familiar with these definitions at the bottom for each of the various inputs. I want my students to have more than just a plug-and-play mentality and understanding of time value of money. I want you to try to develop more of an intuition about what's happening. I don't want the formulas themselves don't need to be some black box that you plug numbers into, but should be a tool for you to take the real-world problems that we'll look at and then solve them using these basic formulas. We're going to start with the future value of a dollar, and if you would just look at your sheet here, let me explain it. First of all, you see the heading that shows the application. The next is a graphic where I'm going to draw a picture, and I want you to do that as well, that will help to demonstrate what's really happening here. I'm going to call it the Snowball Sheet because I think that's a very good analogy here. Formula, there's the mathematical model for each of these applications. Then what I call the usable form. Ultimately I want you to be able to take narrative, sometimes complex problems, and then to solve those using these building blocks here. But I expect you to be able to use a calculator, a financial calculator, and so specifically I'm teaching through the Texas Instrument BA2 Plus calculator, which can be obtained as a calculator or as an application for your iPad. Then we'll walk through an example after demonstrating the model, and then walk through some examples, and then after we finish future value of a dollar, go to present value of a dollar. Now I'm going to spend a bit more time on the future value of a dollar because it is a foundation, let's say the starting point, and if you can understand that and develop that gut feel in a more familiar type of application, I think it's going to go a long way toward helping you develop that intuition, or have that intuition when the time comes when we get to some applications that may not be quite as intuitive as others. Well, let's see what the graphic is. For the future value of a dollar, I have to watch myself here to make sure I'm in the middle of the screen. Future value of a dollar. The future value of a dollar is very familiar with us. Let's imagine we've got a snow-covered hill and a snowball at the top, and as we push that snowball and it starts rolling down the hill, of course snow is added to that. It coheres or sticks to it, and so the snowball at the bottom is of course much larger. We call this, in investment terms or in time value of money terms, that's a PV, a present value. This represents a future value. And the relationship between present value and future value in this application is defined by this formula. The future value at the end of n periods is the present value times 1 plus I raised to the nth power. So there's the mathematical model, but it doesn't make any sense unless you understand what these inputs represent. So please note, the future value is the value at the end of the investment term. That's the size of this snowball at the bottom of the hill, or the amount the investment is worth at the end of the investment term. The present value is the value at the beginning of the investment term, oftentimes referred to as the initial outlay, the amount that you invest at the inception of the investment period. I represents the periodic rate of return, and this is defined as the annual rate. Let me write it here. I equals the annual rate of return divided by the number of times compounding takes place each year. Okay? That says the number of times compounding takes place each year. So that's going to give us our periodic rate of return, or I here. And N represents the total number of times compounding takes place over the investment term. In this particular application, oh, by the way, the usable form we'll get to in just a minute. Let's go ahead and spend some time with this application and see, make sure we have an understanding of what's going on here. In this particular problem, it says, the example says, assume you invest $10,000 for 5 years at 10% compounded annually. How much will you have at the end? That is, at the end of that 5-year investment term. Well, $10,000 represents the invested amount, so that's our present value. 1 plus I. Now, I in this case is the annual rate. That's 10% divided by the number of times compounding takes place each year. And since it says that interest is compounded annually, that's once a year, so I equals the annual rate, in this case, of 10%. Now notice we have to input that in decimal terms here. We're dealing with mathematics, so be careful about that. We do switch back and forth in these problems between percent form, like 1, 0, and the percent sign, versus the decimal form here. But anyway, there's I. The N in this case, it says, and let's look at the definition, the total number of times compounding takes place each year. So if it takes place annually, once a year, for 5 years, N is equal to 5. And so there we go. Well, mathematically, of course, we have to solve for this first. We might combine these terms here and then raise that to the 5th power. So 1.1 raised to the 5th power. And by the way, if you have a financial, well, most calculators, you would probably solve for that by inputting the 0.10, and then you probably got a y to the x key. In other words, you're taking 10%, raising it to, in this case, the 5th power, and then hit the equal sign, and that would give you what really represents the future value interest factor of $1. If you've ever worked with those future value, time value of money tables, future value of $1, present value of $1, future value of annuity, and that sort of thing, you would go to that future value of $1 table, and you would go to 10%. Let's see how it usually is. 10% maybe along the top, the interest rates along the top, 10% and then down 5 periods. And if you did, you would find this value, which is 1.61051. If you wonder how many decimal places to carry it out, just carry out as many as you can. At the end, we can round those off. If it's dollar amounts, in most cases it's safe for my purposes to round to the nearest dollar. If it's interest rates, to the nearest 1/10%. We'll deal with that some later on. But notice this represents then the future value interest factor of $1 that you would find on a time value of money table. But we're not going to deal with tables here. They really restrict us too much in terms of the variety of the combinations of N and I that we can deal with. So that's where the calculator comes in really handy. But here's what this result is. This says if we invest $10,000, okay, here, and we invest that to earn 10% annually for 5 periods, then at the end of that period, the future value will be $16,105.10. Now, let's take a quick look at what's happening here.